everybody. I'm Özgür Martin. I work in Mimar Sinan University in Istanbul. And I'm here in Europe with a grant from SIMPA, and I'm going to talk about stochastic optimization for large-scale machine learning for 4 days, 2 hours a day from until Thursday. I am actually a pure mathematician and mathematical analyst. I work on function analysis, and recently I got interested in optimization and machine learning. It's a little bit different than regular classical machine learning, so we will see what's the difference in a way today. Although the name says stochastic optimization, we are going to look at hi. Camera is running away from me. Look at gradient methods and their variants this week, and their applications in machine learning and deep learning actually. I'm not an expert in machine learning. I just worked on it on its applications a little bit. So if you ask questions on that, I may not be able to answer those. I have been mostly interested in optimization methods that are used in machine learning, and especially gradient methods. But if I cannot answer any question, I can look it up and try to answer it even the next day. So we will have time for that. So let me get back to the slides. We will go with the slides for a while. So, and I, of course, thank SIMPA for giving me this opportunity. All right, so we are going to talk about application. We are going to talk about training machine learning models. And when I say training, actually, it is an optimization problem. So optimization comes into play when you try to train these models and learn certain behavior relations inside the data. So I'm going to start with this very concrete example, CIFAR-10 dataset. As you can see on the slide, actually it consists of 60,000 30 by 30 color images, and these photos are from 10 classes like bird, truck, frog, and there's 6,000 images per class. So the problem today is how do we make a machine learning model to learn these labels by looking at these photos. So when I say that, okay, let's try to put it into some formal definitions. So when I say a data set, actually it will be a set of when I say images, actually I'm going to see them as a sequence of images, and each sequence is actually a vector with dimension dx, and you can think about each of these points as pixels in the image. All right, and then we have these labels about which class they belong to, and it's another sequence of n many points. Mm-hmm.
The camera.
All right. Okay.
You should try to go back and stay a bit,
mm-hmm.
a bit on the screen.
All right. Mm-hmm. All right. Thank you. Let's see. Hopefully it won't switch again. All right. So. All right. So, and then we have a same number of points and labels, and then there are 10 labels. So we will think about them as just integers from 1 to 10. So our problem is looking at these pixels. Can we learn how to guess these labels. So when I say a data set, actually I'm looking at these combinations of these two sets, the sequences. So xi, yi. So in this problem, they are in this space, and I have n many points. In this problem, it was 60,000 points, and each xi has a dimension of 3072. It's 32 by 32, and then times 3 because we have colors, so it's 2 values for red, green, and blue. That's how you denote them in computers. All right. So our problem is we want to find a function, basically, which looks at the space of these photos, these pixels, and spits out outputs and value from 1 to 10, an integer from 1 to 10, which gives us the label of the picture. And we want this function to give us the right label most of the time. Probably not all the time, but most of the time we want to do that. And so here is an prediction function, this an example for age. This is an image from Wikipedia. This is a very simplified version of an artificial neural network. I'm not going to go into details with these networks, but these networks consist of these nodes, which actually are very simple functions like threshold functions, piecewise linear functions, or a sigmoid function. And then there are connections between these nodes, and each connection actually gets the output of this node and multiplies it with a weight and then feeds it into the next node, denoted by these arrows. And then, so it's a very complicated function, not this one maybe, but if you increase the number of nodes and weights, these connections, then it turns into a huge function. And in modern applications, actually, there are millions of weights, these rows, and thousands, maybe more, 10,000s of nodes. I'm not really sure, but millions of weights, I'm sure of that, 20 million, 40 million, maybe even more. So this is a very simple representation of these. So when I say a prediction function h, I'm talking about a function like this, a complicated one, and we are talking about large-scale machine learning problems. So when I say that, the number of parameters is in millions, and the number of points in the data set are in millions also in these modern applications of machine learning and deep learning, of course. All right. So, okay, this is a simple model, but let's see how it works. Actually, you take a image, it's a vector, right, of pixels. Then you feed each pixel into the value of that pixel into these nodes. So those will be the inputs. And then after these calculations of these nodes and then multiplying with weights and feeding them into the next nodes, you will have an output from 1 to 10. We will call it h of xi. And we hope that the output of h of xi is equals to yi for many, many i's, most of the i's. All right. And let's see, okay, the thing is, when we have a neural network like this, most of the time we don't change the functions inside the nodes, they are fixed. But what we do is we change these weights, and then by changing these weights, we want to come up with a function which predicts the right label most of the time. So the question of today and this week is, how do we do that? How do we change weights so that it spits out the right label for most of the time? So basically what we want to do is actually it's an optimization problem. What we want to do is, okay, this fancy 1 is a function which outputs 1 if whatever inside it is true, and it outputs 0 otherwise. And we look at the sum, the average of the sum, that this takes 1 whenever our output does not equal to the real correct output, yi, and we look at the number of those and average them. It doesn't matter. And then we look for the function h, this prediction function h, such that it minimizes this function. So minimizes means less and less errors. That's our problem. But okay, when you have a function like this is not continuous, not differentiable. It's not a nice function, and it's not easy to minimize those kind of functions. So what we do is, to make it easier, and also another problem is, we say a prediction function, but that's a really vague definition of what kind of model, how to choose the right model, how to choose the right parameters. So instead of leaving us, any possible prediction model, what we are going to say is we are going to limit ourselves at specific kind where the family is dependent on a weight, W. I'm going to denote the weights by W. So this is my family of prediction functions. So in a way, they have a fixed form, but we are going to change the weights iteratively so that we find kind of the minimum of this function, or approximately the minimum of that function. All right, but another problem is this function is not continuous. Sorry, I'm going too much to the side, and all right. All right, I need to remember to check the camera. So this is a discontinuous function, highly discontinuous. So we want to, instead of looking at minimizing a function like that, we want to change the functions such that it's continuous, maybe differentiable, hopefully differentiable, and at least for this class, and it still does the thing that we want. Minimizing that function, it still gives us the right answer, and then our model predicts the right labels. So instead of this fancy 1 function, we are going to use an L for a loss function, such that it approximates this function 1, and we turn this minimization optimization problem into this one. So we want to minimize over these parameters, find the right parameter to minimize this function, where the function is continuous and hopefully differentiable. And we are going to look at ways to minimize these functions. All right, as an example of a loss function, okay, the simplest one is at least square sum, where you look at the difference of our output, the model's output, and the real output, correct output. You look at the difference and then square it and then add these up. So if you find a value that minimizes this, then that means h either okay, then that means it gets values close to the output yi, hopefully, and then it gives us the right label. So we are, by looking at this, since we turn it into a continuous function, whichever integer it is close to the prediction function, we are going to say, okay, this is closer to 8, so probably the output is 8. So we guess 8 for that picture, the 8 label for that picture. All right, so let's try to put this in a more compact form, and I don't want to deal with this L and H all the time. Okay, so I'm going to call, okay, let's see. I'm going to call these functions L, H of xi and omega and yi as just fi depending on omega, and its I means I'm using the ith input and ith output. So fi is just the composition of the loss function and the prediction function. So I'm looking at this value, I'm averaging these all, and then I'm trying to find the parameters which minimizes this function. I'm going to call this average as capital F of omega. And I have a sum of n because I have n many data points. So in this form, it is a finite sum optimization problem. And that's how we are going to call it. Okay, so how do we solve these minimization problems, optimization problems? Okay, so as you can guess, it's not easy to give analytic solution for this. It's impossible. So what we do is we use numerical methods, so iterative numerical methods. And the idea is we are going to, since I'm going to assume that these functions are differentiable, so the first derivatives exist. So how do we solve these iteratively? Basically, we are going to start at some point, some initial point. You can choose it randomly. You may have some very clever idea to know where to start, or you may have a lot of experience in that. So I don't know how they choose it. When I try, I usually choose it randomly when I try my models for optimization. So the thing is, what you do, maybe what we are going to do is, so let's say these are the level curves of a complicated function, and we start at some point omega 1, and then let's say this is where the function equals 1, equals 2, and 3. These are the level curves. So when you start at some function, what you want to do is you want to move, you want to take a small step to the direction where the function decreases. And from calculus, we know that if you look at the gradient of this function at this point, this is a vector, right, given in my slides. Actually, it is the vector which, it's the direction where the function increases the fastest. So what you want is, you don't want to go at that point, you want to go opposite point. So you want to go negative in the direction of the negative, opposite direction of the gradient. All right, but as you can guess quickly, there's a problem of how big a step you should take. Because if you look at a function like this, and you want to, let's say, find this minimum point, and you start here, and you look at the derivative, and the derivative is negative, so you want to move in the positive direction, positive x direction, so you want to move this way. So the big problem is how much you should move. Because, okay, maybe to make it a little bit simpler, let's say this is the function. And then if you move this way, okay, that's a nice way to move because here is the minimum of this function. But if you move too much, then actually you increase the value of the function. So if you start from omega 1, you move to omega 2. Now the point you reached has a value, function value bigger than the previous one. So what you want to do is you don't want to maybe take big steps and move a little bit to the right so that you reach to a point which has a smaller function value, and hopefully by doing this many times, you get closer and closer to this global or local minimum point. But actually it's a hard problem to decide what the step size should be. We are going to talk about these in this course. But what you know is, since the derivative is, okay, since you move to the direction of the negative gradient, if the gradient is not zero and the function is differentiable, in that direction there is at least one point that the function gets smaller value. So okay, at least there is one. So the problem is how to find that, and there is no easy way to do that. So we will look at some techniques, so that we can move iteratively and then hopefully reach to a local minimum point. But in this class, since we are going to talk about deep learning models, whenever I have a machine learning problem, what I will have in mind is a deep learning problem, because that's really where the large scale models are. So those functions are really complicated. They are highly non-convex. Because of that, actually you don't even dream that you reach to a global minimum. What you want is you want to reach to a local minimum. And actually that's not what we are going to prove. Actually what we are going to prove is our methods will go to and converge to a stationary point. That is a local minimum, is of course a stationary point, but a point like this, like 0.0 for function x cubed, where the derivative is 0, but you don't have a local minima or maxima. Those kind of points are also a stationary point. What we are going to guarantee is, with our methods today, hopefully, and also in the previous days, looking at new models, new ways, new methods, algorithms to find these minimums, we are going to prove that our method converges to a stationary point, either something like this or something like that. Right? That's the best we can do, at least in this class. All right, so let's move on. So I'm trying to make the camera follow me. All right. Great. So we are going to move in the negative direction, the opposite direction of the gradient, iteratively, with some small or big step size. All right, let's see. And okay. And one thing is, okay, as I told you, our main problem is, mostly we are going to talk about this optimization problem for finite sums. And since this gradient taking derivative is derivative operators are linear, derivative operator, let's say, is linear, the gradient of our function is the average of gradient all the functions that it's made of. So we can easily calculate the gradient of our objective function, capital F, by means of gradient of small f i's. All right. So gradient descent method is actually what I explained you. I think it dates back to Cauchy. Yeah, I think he's the first one suggesting this method, finding minima of functions, complicated functions, numerically, iteratively. So as I told you, we are going to start with an initial point given to us, or we just give it to the algorithm. And then from that point, what we are going to do is, at that point, we are going to calculate the derivative, multiply it with the step size, and then move in the negative direction, in the opposite direction of that point. So we are going to subtract alpha k, gradient of f w omega k from omega k, and then we reach our next destination, omega k plus 1, all right? And then at that point, we are going to do this thing again. We are going to calculate the gradient, multiply it with negative alpha k. Alpha k may change, may be the same from step to step, but for each step, we are going to choose a step size and then subtract it from the current point wk. And after doing it sufficiently many times, hopefully we are going to reach the minimum of that, some minimum, local minimum, or some stationary point of that function. And again, since we are dealing with these non-convex functions, we can only guarantee convergence to stationary points, but maybe we can look at more structured models like convex functions or strongly convex functions, where you can talk about reaching to the global minimum. All right. So this is how my representation of how the gradient descent method works. But here's the thing, this is our gradient. Every time we take a step, we calculate this gradient, and actually what we are really doing is we are calculating the gradient of our model loss function composed with our prediction model. And if you remember, our prediction models are huge functions with a lot of parameters. And then we do this for n times, where n is the number of points that we have. And modern applications, we have millions of points. So for each of these points, we calculate the gradient of this complicated function and add them up, take the average. And as you can guess, this takes a lot of time, because in modern machine learning applications, both n, the number of points, data points, and d, the dimension of the parameter space, both of those values are very large. So because of that, gradient descent method is impractical for these machine learning optimization problems, large-scale machine learning optimization problems. So what we need to do is we need to come up with an idea so that we can do this in a recent amount, acceptable amount of time. And whenever you may think of a problem which is not very easy, it costs a lot of computation time, then you will hear the word stochastic. Let's do it in a stochastic way. Let's do this with random steps, random things that we choose. So we are going to do that also here. So we are going to make our algorithm stochastic. So we are going to randomize it. How can we randomize it with this problem? Okay, we have two big problems here. The weights have a huge dimension d, and the number of this function, this finite sum, has a huge number of n. So you can I think there are methods that you choose random indices from these parameters, coordinates of these parameters, and then you just use those to move, like coordinate descent. That's one way to go. What we are going to do is, instead of doing that, we are going to approximate this gradient, this huge gradient, with something, with an approximation. So what we are going to do is, instead of calculating the gradient for all the data points, I'm just going to calculate the gradient of the function fi, just for one data point, right? So here's a stochastic gradient descent. I think it first was introduced around 1958, but I forgot the name. Sorry who introduced it. I can give it tomorrow. Okay, we start from an initial point, omega 1, and then at each step, again, we are going to choose a step size. Cannot get rid of that. But instead of calculating gradient for all the data points, I'm going to choose only one data point from my training set randomly with respect to uniform distribution. So I'm just going to choose an index, ik, between 1 and n, randomly uniform with uniform distribution from the uniform distribution. All right. Then I'm going to use the gradient of the loss function for just for the ikth data point, and use that to move in, use the opposite direction, multiply it with alpha k, and then use that to move to the next point. That's one way to do that. And you may say, okay, this is crazy. Because we are using just one of those millions of functions to move, but it works very crazily. It works. And sometimes, since this is sometimes a very bad approximation for the real value of the gradient, sometimes you want to make it a little bit better, so that instead of choosing only one data point, you choose maybe 100, 200 of them, if you want more. But actually, I'm going to talk about that hopefully today, that actually you shouldn't choose a lot of them. You just choose 100 or 200 maybe, and then you calculate this gradients and average them just for this subset. I'm going to call it a mini batch. For this mini batch, subset of the integers from 1 to n, you choose a small mini batch. So it's the name, as the name suggests, and then take the average for data points corresponding to those indices and move in that direction of the gradient. And as I say, it sounds implausible, but it works, and it works better. That's what we are going to talk about today, why it works better. I'm just will try to give you some intuition. But if you look at the picture, okay, this is my representation of how it works, but it gives you some idea, and my idea at least, that when you do move with these stochastic gradients, they are approximations to the real gradient. So sometimes they point at the right direction, sometimes not, right? And what you will see if you picture how these points, how this algorithm moves from one point to other, this is the picture that you are going to see, that at first, okay, it won't move as perfect as the gradient descent, but it will work pretty nice until it reaches to a neighborhood of the minima or stationary point. Then it will really wander around, depending on how you choose the step size alpha k's at those iterations. So this is the picture, and I'm going to try to give you an intuition how this works, why you get pictures like this, why it works pretty good at first, even though you are using only one function to approximate the real gradient. It works pretty well for a while, and then it suffers a little bit around the stationary point. And even though it doesn't, okay, maybe I should look at it, it doesn't go directly, not directly, but as directly as the gradient descent. And gradient descent can be shown that it actually finds the stationary point. Here it wanders around the stationary point. But the thing is, with these large-scale machine learning problems, or in general with machine learning problems, you are not really interested in the exact value of the minimum, because it usually gives you overfitting. So I'm going to talk about overfitting a little bit later on. So you don't really want to go to the exact minimum or the global minimum. You want some local minima, or you want to get close to some local minima, which works. And with these large-scale deep learning problems, those models, those functions are very crazy. But in some work, recent work, it was shown that actually local minima that you get to, most of the time they give you a pretty good value for the minimum, a pretty good point, a minima point. So this is acceptable, and sometimes it is desirable, this picture of how it works. So hopefully I'll give you some intuition, at least the little intuition I have. I'm not an expert in machine learning. So I'll start with try to understand why this works like this, a little bit intuition, and then I'll try to formalize the question a little bit more, a little bit better, and then I'll try to show you why this method really converges to a stationary point. I want to prove that today. So this is one way, a toy example, to understand why stochastic gradient descent works how I show it. At first it works pretty well, and then around this minimum point, let's say, it wanders around. So why that happens? Actually, that region where the where the algorithm wanders around, it's called the region of confusion. And what happens is, here's a toy example of what is going on. So again, our function is a finite sum, and it consists of, let's say, these very simple functions of quadratic functions, just a toy example. And each of these has the minima, let's say omega 1 star. And okay, this is omega 2 star. And then we start with initial point omega 1. And okay, we want to find the minima of the averages of all of these functions. All right, the idea here is why it works pretty well at the beginning is, okay, you are here away from this region where these minimas of these individual functions live. So out of that region, which we call the region of confusion, if you're far away from that region, or out of that region, whichever function you choose, let's choose the second one. Okay. And let's assume that it goes like this. So eventually it will go to the left, right? These are quadratic functions, but let's deform it a little bit so it does it inside the blackboard. So when you look at any function, any of these functions, it doesn't matter which one, any of these functions, if you look at the derivative at omega 1 at our initial point, actually, okay, where is the real minimum of the average of these functions is somewhere here in this region of confusion. So if you look at the derivative here, all of them has a negative derivative. So all of them will tell you to move to the right. So little or big, if you move to the right, you get closer to the local minimum of the averages. So you get into the region of confusion. So all of them will direct you to the right direction. But once you are inside, let's say at step K, you're inside the region of confusion. Now, most of these functions, or at least half of these functions, or most of these functions, they will direct you to the wrong direction, right? Okay, let's say this is the real minima of the averages, not the of these functions, but of the average. So most of these functions, if you take this one or this one or this one, they will direct you, okay, these are fine, but if you choose something at the right of this function or this function, the derivatives are always negative, so they will direct you to the opposite direction, to the wrong direction. So here, when you do this, you will wander around. You will choose a wrong one, you will go to the wrong way, and hopefully next time you will choose a right one, and you will come back, and so on. This is why it's called the region of confusion. Depending on how you choose your step sizes, you will keep on wandering around in this region of confusion. There's a way to solve this problem where you choose your step sizes as a diminishing sequence. And if you do it in the right speed, you can prove that actually convergence to the stationary point in this question to the right global minimum. But then sometimes you will move very slowly and it won't satisfy you. That solution won't satisfy you also. So we are going to talk about that also when the time comes. All right. Okay. Okay, let me explain you the problem in more mathematically, and then we will maybe take a break, and then I'll let you ask some questions in a few minutes. So, a more formal introduction, what we are trying to do. We are trying to find a prediction function h from the input space x to the output space y, such that you choose a sample from this space xy, and actually you choose that with respect to a joint probability distribution function pxy. And what you want is you want your h to output a value which is very close to the right output. That's our problem. How to choose an h which does that? The problem with this is we don't know what this, most of the time, we don't know what this probability distribution is. So this is, in terms of this is what we really want to do. This is the problem that we really want to solve. We want to find the minimum of this expected risk, which is the expected value of this function, or the probability of h not equals to y. So you want to minimize these functions. But the problem with these functions, the calculation of these functions depend on the probability distribution, and we don't know that. So what we want to do is we want to find, instead of solving this problem, we will solve another problem which gives an acceptable solution to this problem. So as you will remember, this function that we are going to minimize actually what is called the empirical risk and Rn of h. So we want to minimize this function, which is this finite sum, right? So we will learn how to solve this problem, this finite sum problem, and hopefully it will give a value, a minima, which also works, which is close to the minimum of this expected risk, minimizing the expected risk problem. And when I say xi, yi, these are endpoints that are infinitely drawn from this input times the output space with respect to this distribution. So this is the machine learning problem, right? You have this data, you assume that they are independently drawn from this distribution, and by looking at this data only, by minimizing this function, you want to find the real relationship between these features, these pixels, whatever your problem is about, and the output value. It can be a real value like a regression problem, or it can be a classification problem that we gave an example in the beginning. So we will be mainly interested in this problem of minimizing the empirical risk function defined by this data points. As before, we are going to choose our prediction function. We want to find a function that minimizes that finite sum, but to make things easier, life easier for us, we are going to choose it from a space of prediction functions which are determined by a parameter omega in RD. And then instead of using this one function, indicator function, we are going to use an approximation for that called the loss function. And then our expected risk problem turns into this. This is the expected value of this composition. And then instead of solving this, actually we are going to solve this empirical risk problem. And I'm going to talk about why solving the empirical risk problem gives you an good enough solution for the expected risk problem. What is the connection? So I'm just going to simplify the notation a little bit. All right, so I'm going to see this problem like this. I'm going to use Kc as a random variable. It can be a random seed, right? Because let's say we have a data set depending on indices from 1 to n, and Kc will give you a random seed. We choose one point from this data points, or it will choose a bunch of points like in the mini batch problem. In general, we can think about Kc as a random variable whose realization is not just an index, but maybe a point from the space, input times output space, or a set of points from the space. And our function f will be the composition of loss function and the prediction function. And fi will be it will be the loss again, it's the loss composition, the prediction function, but calculated at the point xi, yi. Because ci will choose a point xi, yi, and then you calculate the loss at that point for your model and depending on your parameters. So our expected risk problem turns into the minimizing the expected value of this general function f, and the empirical risk turns into minimizing this finite sum. So this is the notation that I'm going to use. I'm going to forget about L and H. I'm just going to see all of this as Fi. It depends on the parameter omega, and I means either you choose one point from this space, input output space, or you choose, a bunch of points, a mini batch for that, and then you calculate the average loss for those points. This is the notation. All right, maybe it's time to take a break here. All right, welcome back. So this is where we left off, if the camera follows me. Where we left off last time. So basically, we formalize our problem into this. We have an input space x and output space y. We have a probability function pxy, joint probability function pxy, which chooses these data points. So actually, this probability function gives you the relation between x and y's. Well, for which x you get a y, what kind of a y. So it's actually that's what we need, but we don't know that. What we want to do is we want to come up with this prediction function h. And a loss function L such that this function f gives you the loss. How actually it tells you how well your prediction function does on each data point, for if you use it as fi, or you can leave it like this, and you can talk about the expected value of this function with respect to this random variable xi. So either we minimize the expected risk problem given by this expected value, or this empirical risk problem, which is just a finite sum function, and we want to minimize that. So again, this class, most of the time, we will try to minimize these kind of functions with stochastic gradient descent or variants of those. All right, so as I told you, actually, our real problem is minimizing the expected risk. What we cannot do that because we need to calculate the expected value of this function with respect to a distribution that we don't know. So instead of that, what we do is we use the empirical risk, and we hope, not really hope that, but we can show that actually it gives you a nice solution, good enough solution for the expected risk problem also, minimization of the expected risk problem also. So, but how do you measure how close your solution to the real solution to the expected risk problem? It's not easy to say, and it's not easy to calculate. Even I may give you some estimates, but even those are hard to calculate. So what people do in practice is actually they take, okay, you start with these sample points. That's how you learn. This is supervised learning. I didn't say it before, but what you do is actually in practice, you only use the data. You divide the data into two. You choose a subset of these as training points. It's like 70% of the data points, 80% of the data points, depending on your application again. And then the rest is test points. And then what you do is you choose a model, then you choose an optimization method which finds the minimum value to this finite set problem for the training points. And then you want to know how good of a solution it is. And what you do is, once you fix your prediction function and the correct weights, which minimizes this problem, you check that value, that minimizer, on this finite sum function, loss function, for the test points. These test points you didn't see before. You just put it aside, solve the training, find the minimum of the training function, and see how good it is for the testing function. In practice, that's what people do. All right. So in a way, if you look at it this way, our problem is not finding the best minimizer for the training function, but what we really want to do is we want to find the best minimizer for the testing function, so that we know that this minimizer generalizes well. So our real problem is finding the minimum of the testing function, but you cannot just go and find it. You cannot apply all your nice methods, favorite methods, to this function. You have to do it to this one, get the minimum of this, and see how well it behaves, that point, behaves on this one, right? So that is our problem, and that's what it separates these problems from the classical ones, where you really want to find the best minimizer of some function. You don't want that. You want to find a function. You want to find the minimum of this function by just using this function. That's our problem, and this tells you how good of a generalization your model has, and this tells you how close to how close you are to the real solution of the real problem, which is the minimization of the expected risk. All right, so that's what we are going to do. So if you look at the problem like this, trying to find the minimum, a good minima for the testing function by just using the training function. If you look at the problem like this, then something, surprising for me happens. Okay, so let's remember that I was talking about gradient descent. I said it converges to a stationary point for sure, not just wanders around it. And it goes there pretty fast, actually. And the problem with that, I said, is calculating the real gradient of using all the data points. It's very, very expensive in terms of computer calculation time. So you cannot do that. But when I started this working on this area, I was thinking, okay, these companies, they have a lot of computation power, right? And a lot of computers. Why don't they just, calculate the gradient, using many computers in parallel, right? Because calculating gradient is just calculating gradient for these small functions, fi's, and then averaging them. So calculating the gradient of each fi takes some time, but if you take 100 of them, give it to this computer and another 100 to this computer, get the outputs and then average them, then you can do it pretty fast if you have, let's say, hundreds of computers, fast computers. And these big companies, tech companies, do have that. And I was thinking, why don't they do it? Why they are still working with these stochastic methods, but not on parallelization? And then I saw this paper of Keskar, I think that's how it's pronounced, et al., from 2017, that actually, okay, this has been experimentally observed that actually stochastic gradient methods, they work better than the gradient methods. It's not just that they work faster, but they work better. They find a better minima point for the testing function, not for the training function. But the point they find is works better on the testing function, which you cannot use during the training, during the optimization process. So why is that? And this paper gives you a good intuition on that. So here, as I said, you have data points, you divide them into two, training and then testing. And so you have two functions, but they come from the same distribution. So those points look alike. They are very, very correlated. So if you look at the training function and the testing function, of course, they are not the same, but they are very correlated. And in a way, they look similar to each other, but a little bit off, right? It's like a perturbation. So what these people observed is there are two kinds of minima. They talk about flat minimums or sharp minimum points. Flat minima, sharp minima, where a flat minima is a minima where you have a flat minimum point here. I don't know how to explain. So it's much wider, and then you have a sharp minima like this. It's like a deep valley, and you can see that. And okay, let's look at these two functions. This is the testing function, and then you see in red dashed lines of testing function. They look pretty similar, but it's a little bit, perturbed. And okay, this is a toy example because our functions have millions of dimensions. This is just one variable functions. But okay, here's the idea. Stochastic gradient descent tends to find these flat minimum, and gradient descent, deterministic methods, they tend to find sharp minimum points. And then if you look at this, let's say you found this flat minimum of the training function and you use it for the testing function. As you can see, at this point, this is also a point which is very close to the minimum of the testing function, right? It's just the value just is a little bit up, not much. But if you find a sharp minimum, as you can see, you find this sharp minima point for the training function, and you apply it, you calculate the value of the testing function at that point. Now the function value goes really high, because even a small perturbation really disturbs the value, the minima characterization of this point. So this is why a flat minimum works better for the testing function. And stochastic gradient descent, stochastic methods tends to find them. That's why stochastic gradient descent, it's the simplest, maybe the simplest, one of the simplest methods in the literature that looks for minima points. But it's very, very popular because of this, because it's very successful finding the minimum of the testing function, all right? Not the training function, because it generalizes well. That's how the machine learning people call it, because they tend to find this flat minimum. And experimentally in this paper, Keskar et al. In 2017, this is what they do in this work. Experimentally, they go and find, they use SGD, stochastic gradient descent, to find the minima. And then they use gradient descent to find the minima. And then they draw a line. Okay, this is a function with millions of variables, but you can draw a line from one point to the other. And then through that line, over that line, they calculate the values of the training function and the testing function. And also they look at the accuracy anyway. So this is the shape of the training function between the minima which given by the stochastic gradient descent and the minima given by the gradient descent. And as you can see, stochastic gradient descent tends to find a minima, a flat minima, and gradient descent tends to find sharp minima. And they made a lot of experiments on this, and they came up with this conclusion. So that's why, even though it's a stochastic process, even though it just uses an approximation, maybe even a bad approximation of gradients for the real, of partial gradients for the real gradient, and it works faster, and it finds better minima, which generalizes better. So that's why stochastic gradient descent, even though it's very simple, it is a very popular algorithm. It is still in use widely for training deep learning models. But the big problem with stochastic gradient descent is, as you already asked, it's about how to, hopefully you can still hear me. All right, it's about how to come up with the right learning rates, step sizes. That's a huge problem, and it takes a lot of, it makes training these, this difficulty makes training these machine learning problems, deep learning problems, take a lot of time. I'm talking about 1,000 days, hundreds of thousand days of CPU computation time. That's so people are always trying to come up with better methods and or come up with better ways to adjust the learning rate of the stochastic gradient descent. And some people are looking at other approaches, so hopefully we are going to see some examples of those. And I should warn you that the things that I'm going to talk in this course is actually depends on my path, my adventures in stochastic optimization in machine learning. So it's path dependent. It's what I saw, what I liked. It depends on that. So there are many methods that I won't cover. It's no way a comprehensive introduction, but it's just an introduction. Hopefully it will give you some good intuition and some insight into the mathematical theory of this area. So the winner is the stochastic gradient descent. So we are going to analyze that for a while, and then we will see its variants. Okay, the problem is minimizing a function like this, where the function is either the expected risk function or the empirical risk function. In this class, mostly it will be empirical risk function, this finite sum. And then when okay, so I need to take this. And then I'll define this function g omega k, ck. Actually, it's the gradient, depending on the random variable c on the kth step. It's a k, ck is the realization of the random variable c on the kth step. So it can be two things in this class. Then I'm going to add a third one. It can be two things in this class. Either it is the gradient of only one function on one data point, so just one, realization, or it will, this C will give you a bunch of points, a mini batch, and you're going to calculate the gradient depending on those data points and take the average. So either it is okay, either it's this will be the stochastic gradient descent using one data point or a mini batch of data points. So the analysis is the same or both or very similar. Okay. So here's the algorithm for stochastic gradient descent again. So we start with an initial point. In this class, I don't care how you choose that, but choosing it right really affects the performance as much as I can see and read. And then we choose a maximum iteration number, because this can go on forever. You can get closer and closer to the, or you can just wander around the stationary point. So what in practice people do is they just stop at some point. So this algorithm doesn't stop for you. You can do that, but in practice, actually, people just say, okay, this is enough. I'm going to stop and look at the values. That's what they do. And then we are going to choose step sizes for each of these steps. Okay. So at each step, I'm going to choose generate a realization of the random variable called k, calculate the gradient at one point, depending on k, or at a mini batch. And then once you get an approximation for the real gradient of capital F, I'm going to use it to take a step and move to the next point. That's stochastic gradient descent again. I'm talking about stationary points. Here's a formal definition. It's a point where the gradient of the objective function is 0, right? So it can be a local mean, local max, or it can be, none of them, but it's a stationary point. So most of the time they work. So, and this is what we can guarantee. So most of the time you just converge to a local minima, which works fine for your problem. And this is the L2 norm that hopefully you already know. It's just Euclidean norm of a finite dimensional vector. There's nothing interesting there. This is the notation that I'm going to use for it. So to be able to prove that the stochastic gradient eventually converges to a stationary point, we have to put some assumptions on the function that we are trying to minimize and the corresponding stochastic gradients. So I'll start with this condition, which is called, we will say if objective function is Lipschitz continuous. The gradient of an objective function is Lipschitz continuous with Lipschitz constant L if for any omega and v in this parameter space, the gradients, the norm of the difference of the gradients is smaller than L times the distance between these 2 points. These are L2 norms defined here. All right, so I'm always going to assume that my function is continuously differentiable. So it's okay. I'm done. Okay, I'm here. Follow me. Okay. And actually, I'm just going to assume that it's differentiable and its derivatives, all partial derivatives, are continuous. But if you look at this condition, actually it tells something about the second derivative, even though it may not exist. But if it exists, it tells you something about the curvature. But if it exists, the second derivative exists, actually this says the second derivative is bounded from above by L. All right, but I'm just going to assume continuous differentiability. All right, so under this condition of Lipschitz continuity, actually we will see that it said this function under Lipschitz continuity of the gradient, actually this function satisfies this inequality, very useful inequality that we will use everywhere for any omega and v. So let me prove this, why this is the case. So let's start with that. Now I'm switching to the board to prove that proposition. All right, so I think you can see that. So let me prove this. The proof is simple, actually. It's just calculus of functions of several variables. So you start with f of omega. And all right, so I'm going to rewrite this f of v plus from 0 to 1, the derivative of f of v plus t times omega minus v So the values of f on the line from v to omega, and the derivative of this function with respect to t, and the integral of that with respect to t from 0 to 1. And it's pretty easy to see that actually this thing here is just the value of f of omega minus f of v. Right? So if you add that to this one, you get f of omega. Now, I'm going to rewrite that integral. Okay, it's following me. As this integral from 0 to 1 gradient of f of v plus t times omega minus v transpose omega minus v dt. You can see the equality by just using the chain rule for functions of several variables, so calculus 2. What is this notation? Actually, this is, okay, you cannot see that. Okay, what is this notation? This is just an inner product. So if you have, this is the notation that I'm going to use. So let's say you have a vector a1 up to an, and b, which is b1 up to bn. So a, okay, sorry, not this way. So I'm going to think about vectors as columns. Yes, and b as b1 up to bn. Okay, then A transpose B is just A inner product B, which is, it's just a matrix multiplication. If you transpose this and then multiply it with this one, then you will have A1 B1 plus A and Bn. So it's just denotes the inner product of these two vectors. All right. But I'm going to stick with this notation. It's more, I think it's a more popular notation in this area. All right, unfortunately, I'm going to clean this up. I wrote it in the wrong place. Anyway, sorry about this. Okay. Again, just using the chain rule, you can see that this equals to that. And then this equals to f of v plus, okay, I'm going to add and subtract this value, gradient at v, inner product, transpose times omega minus v. And I put it inside the integral. Since it's from 0 to 1, you can just put it inside. All right. Let's see. Okay. Just you get, okay, if I put these together, because inner products are bilinear with respect to each coordinates, each side. So you can write the first one, sorry, v plus t omega minus v transpose minus gradient of f v transpose. Okay, just put them together and then transpose them. Transpose of a sum is the sum of the transposes, and then omega minus v dt. All right, so I just add and subtracted this term, put one of the negative one inside the integral. But now All right. I'm going to use the Cauchy-Schwarz equation, right? If you remember, let me go here. I hope I'm not boring you with this, but if you remember, A, B, the absolute value of that is smaller, or again, this is A transpose B, is smaller than equal to this, right? So I'm going to use that. So this is smaller than equal to f of b, gradient of f of b, I have gradient f v plus t times omega minus v minus gradient of f of v norm, L2 norm, times omega minus v L2 norm dt. Okay, now at last I'm using the definition of Lipschitz continuity. These are the gradients in a norm at 2 points. Lipschitz continuity tells you that this expression here is smaller than equal to the difference of some L times the difference of these 2 points, v plus t times omega minus v minus v. V will cancel out, so we will have t times omega minus v. And then omega minus v dt. And I'm going to take this scalar t outside. It's a scalar between 0 and 1. It's positive, so I can just take it out. And whatever you have here. All right, then as you can see, everything is a constant except t. This turns out to be t squared over 2 from 0 to 1. It's 1 over 2 times L times omega minus v norm squared, and then this a very simple proof and result actually, but it's extremely useful. We'll use it at everywhere in this class, at every result that we will have. All right. All right, so we will, aside from this proposition, we are going to give our first result about our SGD, the stochastic gradient descent method. Okay, let me define with this ECK, I'm going to denote the expected value taken with respect to the distribution of the random variable CK given the point omega k. So this is this conditional expectation. So I'm not going to use this notation. We are just going to assume every time we take the expected value with respect to CK, this is done given omega k. And this is our first lemma about SGD method, that under our assumption, Lipschitz continuity, okay. Under our assumption of Lipschitz continuity, okay, let's see. Our results will always depend on an expected value because we are working with stochastic gradients and random variables, and we don't know exactly where this stochastic process will go, but we can calculate this expected value. All right, so the theorem says the expected value with respect to k of the point f of the value of f at the point wk plus 1 minus the value of the function at wk in the previous step, the point at the previous step, is smaller or equal to than this expression. All right, let's prove this and then talk about this a little bit. The proof is very quick. It will be very quick. Okay, this was our previous proposition. For any omega, and okay, for any omega and v, f omega is smaller than equal to f of v plus this plus this. Okay, this is the result of the previous proposition. Okay, we are going to use that, of course. Let me rewrite it here, f of omega. Okay, I'm going to use that, not for just omega and v. I'm going to do that use that for omega k plus 1 and omega k. So for any 2 points, in particular for omega k plus 1 and omega k, okay, if I move fv to the left, so if f of omega k is smaller than equal to the gradient of f at omega k transpose times omega k plus 1 minus omega k plus L over 2 times omega k plus 1 minus omega k non squared. It's just the Lipschitz continuity. Proof of the lemma. All right. And what is the definition of this? In the gradient descent, you move from one point to the other by subtracting alpha k times the gradient, approximate gradient. So actually this equals to, this is what? This is negative alpha k g omega k ck. So this equals to, if I take the negative alpha k out of this inner product, then I have gradient f of omega k transpose. What is left is g of omega k k. And then same thing here, I'm going to take alpha k out in this from the square. So this is plus L times alpha k over 2 and g of omega k k non squared. And okay, as you can see, remember that g omega k k is the approximate gradient, stochastic gradient at the point omega k, and stochastic comes from this random variable. So this is either the gradient at one point or a average gradient on a mini batch. All right. All right, and then okay, it looks kind of like that. So now we are going to take expectations, both sides, with respect to k. And remember, k is the random variable that we use to choose a random point at the point k. But at the previous point, we didn't use k, so it's just an independent random variable. It's independent from the previous step. So taking the expectation with k, then this is just a constant for that integral, right? And so anything with omega k is just a constant. So taking expectations, we just take the expectation of the value at k plus 1. Okay, because this point is chosen using ck, and then this is just a constant for that expectation. This is the expectation with respect to ck given omega k. All right, this is smaller than equal to negative alpha k, and the expectation, oh, if I go there, all right, and the expectation of this inner product here. But look at that, expectation of that inner product. Okay. The thing is, the expression on the left, this transpose, only depends on omega k. It doesn't depend on ck. So we can just skip that. So you can check easily that actually this inner product, expectation of this inner product is just the inner product of this term with the expected value of g omega k kc, my awful kc, okay. And then the expectation of this, but this term has k in it, so plus L alpha k over 2, the expected value with respect to ck of the square of this norm. And okay, this is exactly that. So I don't have much time, so I'm going to stop here for today with this lemma. But let's look at this lemma. What does it say? It says, let's assume we are at the point wk, omega k, and then you take a stochastic gradient descent step, and you move to the point omega k plus 1. The expected value of the objective function at this new point that we have moved minus the value at the previous point. Now, since we are at step k, we just assume omega k is given to us, so it's a fixed value. But omega k plus 1, we get it by a stochastic process. So with the expected value of the f of omega plus k plus 1 minus f of omega k is smaller than equal to this expression plus this expression, the second term. The second term is always positive, right? It's the expected value of norm squared of g plus a positive constant L plus alpha k squared, and alpha k is, we assume, then positive, but it's already squared, plus 1 over 2. So this is positive. But what you want is you want to move to a point where you expect that the value of the objective function at that point is smaller than the previous step. So you want this expression on the left to be smaller than equal to 0, hopefully, or something negative even, not just 0. So in order to achieve that, what we want is we want this term to be negative. This already has a negative sign in the front, and alpha k is positive. So what we want is we want this inner product of the gradient at wk. We don't know what that is, but we want the gradient, the real gradient times the expected value of the stochastic gradient to be positive, right? So what we want g to be a descent direction. So we want this inner product to be positive, so that hopefully it's not just negative. We want that positive, but actually we want it to be sufficiently positive, sufficiently bigger than 0, such that this expression is negative, and then if you keep on doing this process, actually it converges, it gets smaller and smaller, this function, and the function converges to a stationary point. So actually, with our approach, we can actually calculate this, and we can show that this is positive. It's very easy, because I'm going to talk about that tomorrow, but the expected value of these gradients is just the gradient of f, right? They are not equal, they are an approximation, but the expected value is exactly gradient of f, capital F. So this will be just, this inner product will be just the norm squared of the gradient of f. So it will be positive, and actually it is, proportional. It's exactly the square of the norm of gradient f, and actually that's enough, nearly enough, to show that this process will converge to a stochastic stationary point. The only problem here is, okay, this is negative, this is positive, so you look at the difference. You don't want the right-hand side to be really big. If this is big, then the sum can be positive, and maybe you are not descending at all. So you want this to be small, sufficiently small. But in general, you cannot guarantee that. To be able to guarantee that, these are the norm, squared norm of the gradients. So it's kind of the variance. You want the variance of these gradients. Their expected values and of half of these stochastic gradients, but you want the variance to be sufficiently small. So next time we meet tomorrow at 2, we are going to put an upper bound on this, assume an upper bound on this. And then with that assumption, we are going to show that actually with that extra assumption, we are going to show that stochastic gradient descent actually converges to a stationary point. But I'm going to stop here for today.